This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And how to implement them, just to have more hands-on experience. Someone asked me about determining when, for family of functions, when the Newton method, we can characterize the region of quadratic convergence for family of functions. Was it you? Someone asked me this question.
Domain of attraction.
Yeah, the domain of attraction. Really, I said for a family of functions, we can write it in a closed form. I said it's related to self-concordant functions. I remembered what it is, but I couldn't remember the reference. Okay. So the set defined by x such that grad of x transpose inverse of the Hessian grad of f is less than 1. This is where we can characterize the domain of convergence for the Newton method for the self-concordant functions. I think it's in one of the books of Nemirovsky and Nesterov. I just couldn't find it. I briefly looked at it. So Arkady Nemirovsky and Yuri Nesterov. Anyway, that's the idea. You can go and look at it. Try to find the source and let me know. Okay. So, let's start from where we left off. So this is the example that we just looked at last time when we investigated some the meaning of, not the meaning, how we can observe. I forgot your cookie. I promised a cookie. I will get it after the break. Observe the numerical performance of these sort of quadratically converging algorithms. Now, what we are going to do next is to now spend some more time on Newton type algorithms and talk about a family of them called BFGS DFB. Just before going forward, there's something else. If you really have some background in linear algebra and you really want to know more, I recommend these two books. This is written by Lloyd Trefethen, which is probably, I don't know, he's one of the top 2 people in numerical algebra methods now. It has still to do, but anyways, he's one of the good ones. And the book is excellent. A bit more advanced is this book by Demo. These are very useful things to know, as in general, not only relevant to this course, but relevant whenever you end up solving complicated problems that requires a bit of programming. It connects the maths to the programming aspects as well, to really understand what we mean by numerical stability, why we do things the way we do them, what are how we can capture sensitivity in these sort of problems. Okay, so that's what we did. Now let's go back here.
example, how do you find the 0.28 and 0.29?
Because I calculated the domain of attraction.
By using the...
Yeah, using the same relationship. You can do it as well, it works out. Then I know if I am on this side, it's going to converge. If I'm just slightly on the other side, it's not going to converge. So it's like a magic trick, which I know the answer to. All right. Okay. And as I said, the convergence proof that I did during the class last time is yet another proof. I prefer that proof to the one that is in your textbook and the one that I put on the slides, because I said it last time. Does anyone remember why I think, at least in my opinion, that proof is a bit better? Did anyone spend time thinking about that proof? Okay. I suggest that you think about stuff that we discussed during the class as well, because again, it doesn't serve any purpose if you don't think about it after the class. The reason that I think the other proof is a bit better is, first, it is independent of the choice of the norm that I am using in terms of the convergence relationships. I don't rely on sufficient optimality conditions at all. I only that proof converges to any stationary point. So it can be applied to saddles and maxima and minima equally. So it's a more general proof. I don't invoke any other extra assumptions. And I can say, I mean, for example, these things sufficiently close to X star. In that proof, we construct what we mean by sufficiently close to X star. So we can give, it sheds more light onto how the algorithm converges really. So it provides more insight. Anyways, the proof is written here as well. It follows a very similar line of reasoning, but it diverges somewhere around here, because I end up using a different sort of idea. Anyways, now what we are going to do today, we start looking at quasi-Newton methods. Quasi or quasi. Can someone tell me what, just from the word, what do we mean by a quasi-Newton method? Rob, can you take a guess? It's something that's similar to Newton, not quite Newton. Can someone tell me why we might be interested in something that is kind of like Newton, but not Newton? What were the components of the Newton's method? What are the iterations of the Newton's method? You two step ahead, but that's the idea. The components of the Newton's method, can someone tell me the iterations for the Newton's method? Han, do you remember anything?
Second directives of
Okay, the iterations of the Newton method look like this. So what are the building blocks of the Newton's method? If I have an oracle, what questions do I ask from the oracle at any point xk? I ask about the gradient, I ask about the Hessian. Okay? So I have to ask two questions. Now, in a quasi-Newton method, we don't want to have a complicated oracle that always answers these two questions. I want to ask fewer questions, but be able to mimic the behavior of the Newton's method somehow. Okay? So what is, in those two questions that I'm asking from the oracle, which one is more challenging? The Hessian is more challenging, right? So we want to replace that question with something else. So that's the idea of a quasi-Newton method. So again, it goes back to now let's try to read this theorem together to understand what it means. So we always start with some assumption on f itself. We need it to be twice continuously differentiable, to be able to take derivative twice. And we are writing the iterations in the general line search style. pk is the direction that we are searching. And we write it like this. Now we are assuming that bk is some symmetric and positive definite matrix. The next step. So we assume bk is positive and semi-definite, a symmetric and positive definite matrix. Just up to this point, what can I conclude about pk? Mark, what is the property of pk, the search direction? It's a descent direction. So up to this point, what we can conclude is pk is a descent direction, right? Now let's continue. Then we say, let's assume that my algorithm converges. So I've applied this sort of iterations on a particular algorithm. And let's assume it converges to some stationary point that satisfies the second order sufficient condition of optimality. Then we know this convergence is superlinear if and only if this limit relationship holds. Now let's break down this theorem. Does it tell us when a general line search method converges or not? Show of hands. How many of you think it establishes the convergence of a line search method with those properties? Okay, so Han, Yushin, Mark, kinda. I mean, it's a binary answer. Did he change her mind? Yes, no, she stuck. How many of you think it doesn't establish convergence? Mark. Oh, okay. A lot. And we have 6, 7 people who sit on the fence. Okay, let's read it together. We assume that if it converges, the convergence has a certain property under a different condition. So a theorem like that does not say the algorithm solves the problem. It says if it can solve it, we can conclude a certain set of conclusions. Okay? So it is very important to be able to read theorems like that to extract the correct amount of the correct information out of it. Now, what it says that now if an algorithm like that solves the problem, by solving, I mean it converges to a point that satisfies the sufficient conditions of optimality, then we can do this test. If this ratio goes to 0, we have superlinear convergence. Can someone tell me what is the importance of superlinear convergence? Can someone tell me what superlinear convergence is?
xp plus 1 minus x star xp minus x star equals 0.
Okay, that's how we define a limit of all, sup lim of all of these things equal to 0. So not just the ratio, lim sup as it goes to infinity. But what it is just a definition. What does it intuitively mean? Okay, what is the family of algorithms that we expect to behave in a linear way, to exhibit linear convergence? Yeah, gradient descent type methods. For the best case, they converge linearly. So it means it's in the hierarchy of rates of convergence, then this method will sit one step above. What is the other family of algorithms that we saw that if they converge, they are going to converge faster than gradient descent? Newton's method. We saw it last week. They sit quadratically. So if I want to imagine these sort of convergences, Newton's method sits here. These sort of quasi-Newton methods sit there, and then the gradient descent sits here. Quasi-Newton methods, by construction, they cannot perform better than a pure Newton's method. They sit somewhere in the middle. There is an order of hierarchy of convergence. Okay? Now, an open question, open problem is really to establish for the general family of functions the convergence of these quasi-Newton methods. But we know that if they converge fast. Okay? So it's a hole in the literature. And some people, I mean, there are different efforts. And for different cases of functions, people have come up with solutions, but it's not, the general theory is not complete yet. Now, let's see the first Newton's type method that we are modifying things a bit. It really eases our way into what we want to discuss next. Okay. In a general pure Newton's method, when we are away from the solution, pk may not be a descent direction. Can someone tell me why is that? Moir, do you know why I can make a statement like this?
I think maybe have a relationship with Hessian.
Yeah, correct. It really depends on the Hessian. The Hessian might not be positive definite far away from the solution. So the pk that is generating might be in a weird direction that is not the gradient descent. Okay? So it's good. That's why. Now, to get around this problem, what we can do, we can try to perturb the Hessian by some symmetric matrix. Okay? If I have a symmetric matrix, let's just, again, intuitively, if I have a symmetric matrix that is not positive definite, if I add a very positive definite matrix to it, what do we expect to happen? Yeah, we expect it to become positive definite. Now, this super vague statement relies on, I don't know which one to mention. There is this sort of family of results called Chi-Fano-Weil interlacing theorems. Depends on that. That's where it comes from. But intuitively, kind of makes sense. But now we can make it a bit more precise. If you want to make it precise, we have to go and look at Chi-Fano-Weil interlacing eigenvalue result. We don't go there. We come up with a simpler explanation for a very specific type of the perturbation matrix. Yeah, okay. Things disappeared. No, they didn't. So that's the proof I did. I have uploaded a nice version of it on LMS. Go and think about this. Don't memorize it, think about it. Again, the other thing as well, the exam, you can bring anything you want to the exam, except something that you can look up, search internet on. That's a bit too much. But you can print anything, you can bring any books you want, you can bring anything you want. So you can take this proof and take it to the exam, but if you don't understand what I did, I will never ask you to reproduce this proof exactly, right? So try to understand what I've written here. Anyways, now let's think about a matrix H. H is not positive definite. Can I conclude it is negative definite? No, because the eigenvalues, some of them can be positive, some of them can be negative. And I can talk about positivity and negativity of eigenvalues because H is symmetric in this context, so the eigenvalues are real, etc., etc. So H is not positive definite, so I write it like this. And let's concoct a matrix E that is rho times identity. Rho is a positive scalar, identity is just the identity matrix of the same dimension as a H. If I add H to this E, can someone tell me what rho needs to be, what condition rho needs to satisfy so that the resulting matrix here is positive definite?
The magnitude has to be greater than H's greatest negative eigenvalue.
So if I take the H's smallest eigenvalue, which is the greatest negative in magnitude, so I'll call that lambda mean. It's a negative number. I pick rho to be strictly larger than this. The resulting matrix is positive definite. So it's an easy fix. I can shift everything to make them positive. Okay? So that's the simple modification that we can have. There are other ways of doing it as well. Again, as I said, I want you to get the idea. We can use other sort of factorization to get to the same result, similar results as well. So we perturb BK if the Hessian is not positive definite. So we end up getting a descent direction when we are far away. And hopefully in the vicinity of the solution, we don't need to do the modifications anymore. And then the pure Newton step kicks in. Okay? So these sort of algorithms are usually called hybrid algorithms. When we are far away from the solution, we do something. When we get closer, we do something else. The reason is we want to take advantage of the global convergence of gradient descent, or steepest descent, and when we are far away, and then quadratic convergence properties of Newton's method when we are close to the solution. Now, I spent some time last week on the meaning of global convergence. Rushin, can you remind us what I mean by global convergence of an algorithm?
It means that the initial value will start from any point from in the domain can converge to its optimal value.
To an optimum solution. Yeah. It doesn't converge to the global solution, it converges to a solution, but we can initialize the algorithm from anywhere in the domain. So Newton's method doesn't have that property. Remember, we have to start close enough under some definition, then we converge. So that's the global convergence property of general descent line search methods. So it's really trying to take advantage of these two sets of properties. Okay. This is a property that we saw last time as well. If the condition number of bk is bounded, so by some c, we call it bounded modified factorization property. We want to make sure that all over b satisfy this property. If that condition holds, then we can show we have convergence to the solution as well. And then I say to the solution, it means to a solution that satisfies the first order necessary condition. It is something else. Maybe we want to use this property to modify our Hessian so that it has this bounded condition number property. So whenever we see any of these theorems, I think it's very important to ask what they mean, right? Because otherwise they will remain as theorems, and we never learn how to use them when we analyze or write algorithms. Okay? So I really ask you to think about it and come and ask questions, what it really means. Because these theorems really should guide anyone who wants to solve optimization problems to come up with better results, better algorithms that have predictable properties. There is a quote, which I can't remember who said it, but I saw it somewhere, and I like it. So designing any engineering solution without understanding the specifications is neither bad or good. It is just surprising. So we don't want to do surprising stuff. We want to understand the behaviors of a particular solution and solving an optimization problem is a solution as well. These theorems guide us to come up with answers that don't surprise us. So we want to avoid surprises. Okay. In the general case, we cannot make any statements about these sort of Koizan-Newton algorithms, their convergence behaviors. They can fall in any category if they converge. For the general case, that we have to take things as I think, again, I'm making a guess based on what I've seen and the existing knowledge in the literature to the best of my knowledge is these sort of Koizan-Newton methods can fall in different categories, and for specific concrete problems, we can try to establish properties, but we can't make statements about the general classes of problems. There are other ways of modifying the Hessian as well, or the inverse of the Hessian. As I said, eigenvalue modification is the easiest one to see because we are just shifting everything by some amount, multiple of identity. But there are we can use these sort of factorization techniques as well, which, if I'm going to talk about those factorizations, we will be spending a lot of time on just establishing those factorization. We will review Cholesky factorization when we talk about solving least squares problems. The key here is that there are other methods of modifying the spectrum of a matrix, and some of those methods can be useful in designing Newton-type algorithms. If you worry about a question in exam, I will not say, explain how to do modified symmetric indefinite factorization implemented, write an algorithm for me. This is not the sort of question I ask in an exam. You can go and look up the previous exams. I've uploaded them to LMS. I will not say establish everything from scratch. I will give you hints if I need to. There will be stages, but this is, don't worry about it. Don't say what happens. All right. So now we caught up on where we left off last time. Now we are going to talk about BFGS. Now we are going to spend more time on quasi-Newton methods. And specifically, I want to talk about BFGS. BFGS is an abbreviation of 4 different names. B is for Broyden. Probably that's the most important name here because I will briefly comment on it. And 3 other people. It is, in my view, the nicest quasi-Newton method, and it has some nice systems theoretic properties as well. If anyone's thought about control and estimation, it has nice interpretation in that domain. Then we talk about limited memory. BFGS is a variant of BFGS with a lot of interesting application, and we will comment on open questions regarding limited memory BFGS. And then we talk about how we can use BFGS-type methods to solve sparse problems or set up distributed solutions for optimization problems. This will be our first go at mentioning distributed optimization. I will revisit it when I talk about dual iterations later. So again, hopefully you will understand the basics of quasi-Newton method by the end of today. You will be able to construct a BFGS algorithm and understand the implementation issues associated with BFGS and limited memory BFGS, and learn how to take advantage of sparsity in problems and how to extend that idea to distributed and parallel solutions to optimization problems. Okay? But to be able to get there, you need to go and think about what we talk in this lecture. Okay? It is very helpful if you go and read some related material from the textbook to this lecture, or at least revise the lecture notes and come and ask questions later. Okay? So when I write things here, it's really for you to go and, there are pointers, you go and think about them after the class. Because no one ever learned anything by just staring at slides. I wish it was true, otherwise I would be very smart. I'm not. Okay. Again, the cliche slide that we've seen it twice probably before, or once, I don't know. We are solving an optimization problem, it's unconstrained. So the implicit assumption is that when I say it's unconstrained, X should belong to the domain of F. But let's assume that's implied. We are picking a line search iteration, we have a step size, we have a search direction. This is exactly what we saw last week. Just say it again because it's good. We call it step length or step size. But now we know, for example, what sort of properties the step size need to satisfy. I call them Wolf conditions. Can someone tell me what they mean? Again, I don't want the exact statements of conditions, but I want if someone can tell me intuitively what those two conditions meant. Can you tell me?
Limit the stem mass not to be too large.
Yes. It's really about not jumping too far ahead and not too close that we don't gain anything. It's to rigorously quantify what we mean by these two statements. And then we show that if these conditions are satisfied and P is a descent direction far away from enough or at not exactly orthogonal to the gradient direction, then everything is fine and we're going to converge. Okay? So that's, I call these conditions as the step length is selected sensibly and pk is not too garbage. Okay? So the family of Quasar-Newton methods now, which might include steepest descent, because what was B in the steepest descent? It was the identity matrix, right? It's like saying, if in Newton's method I don't want to calculate the Hessian, but I always assume the Hessian is identity. It's a coarse estimation of the Hessian of the function, but we end up with the steepest descent. It's a bad estimate, but it results in something that is sensible. And generally, all of these things rely only on the knowledge of the gradient. So they belong to the first order oracle family of methods. And what they do, they try to construct a model of the objective function based on the variations in the gradient of the consecutive steps. So in the language of estimation theory, they are building an estimator that estimates the Hessian of the function based on observed data. If we want to be fancy, we would call them, they are super adaptive online learning algorithms to solve optimization problems. But these things have been around since the 1960s. Okay? So that's what they really do. They try to estimate, and again, if you want to be on the hype bandwagon, they try to learn the Hessian of the cost function as they travel along some trajectory, some path, some sample path to be more precise. Okay? So that's what they do. And the aim is that this extra bit of knowledge allows them to get a convergence that is faster than linear. That's the hope. Otherwise, what was the point of anything that we were doing? Right? So that's another question you always have to ask when designing an algorithm. If you are making it complicated, you have to show the benefits. Because if you're just making something complicated for the sake of it being complicated, it doesn't make any sense. There is a trade-off all the time. So if I make something too complicated, but the benefits are not proportional with the complication I'm introducing, it's worthless. Okay? So we have to be able to quantify this. What do we lose? What do we gain? And that's a lesson in life as well. Here I say we focus on small and medium-sized problems. When I say small or medium size, I don't mean problems with 5 variables. I'm talking about problems with thousands of variables, but not tens of thousands or hundreds of thousands. So in my vocabulary, the small problem is a problem with 500 to 1,000 variables. Okay? And we will see why we focus on this. Hopefully by the end of this lecture, I will show you some examples. Okay, now BFGS method. It's the most popular one. Oh, here we go. The name of the other people on it. It's developed by Broyden, Fletcher, Goldfarb, and Shannon. And it belongs to a family of algorithms called the Broyden class. That's why I said Broyden is the most important name in these four. If anyone is interested in the general Broyden class algorithms, you can go and look it up in the textbook of the course. You two that you just... Did you have a chance to look at the first lecture?
Very basic.
Okay. You know that there is a textbook that you can download from the library, right? Okay. Go ahead and download that, because that's important. Because I really built it on that textbook. There are extra bits and pieces, but the textbook is important. Now, all of you that you've been coming to lecture for the third week now, how many of you have looked up anything in the textbook? Okay, it's better than expected. It's great. Textbooks are very important, especially in advanced subjects. This is an advanced subject, right? It used to be a PhD exclusive subject, but now we open up to masters as well. Because think of it like this. People who wrote these textbooks spent decades on coming up with a way to explain ideas on a piece of paper. Sometimes they fail, but sometimes good textbooks, they become main references. So this is how we can see they are good textbooks. So the ideas are refined, they resonate with people. That's why it's important to go and learn from textbook, because it's the distilled version of someone's knowledge with a lot of experience. You can rely on me as just a pointer to ideas and someone who tries to clarify things, hopefully, if I'm successful. But your main source should be a textbook. Okay? So I'm just a channel. I try to channel that and try to provide some extra insight, sometimes unsuccessfully, but it's very important to go back to the source material. Anyways, I finish my sermon and continue with what's going on here. Now, all of these sort of Koizanian methods rely on some local quadratic approximation of the cost function. That's what Elad alluded to. You said that, right? You did. Around the point. So the idea is that we are at some point xk. We construct a local model of the cost function that looks like that. And then we go and, well, let's just draw some stuff. So I have a function that looks like this. I am at some point here, let's say. Here I construct some quadratic approximation of the cost. This is the quadratic approximation. So this is f. This is some quadratic approximation. I call it m. Now, if someone wants to make a quadratic approximation, forget about anything. First, what does it mean? What form does it take? What is a quadratic approximation? So if I give you a function and I give you a point, x, I say write a function that is a quadratic approximation of this particular function in the vicinity of point x. How would you do it? Someone whispered the answer. It doesn't need to. Didi keeps whispering the answer. Can you say it loudly? It wasn't that loud, but Taylor's theorem, right? So we use the Taylor's series to write some approximation of a function in the vicinity of the point that we are investigating. So I am at point fxk. How do I write it now? What is the second order approximation of this function? Sorry, I meant this. Rob, what is the second order approximation of function? Have you had a chance to look at the first lecture? Yeah. Okay. Can someone tell me what is the Taylor's series in the vicinity of xk? Mark, do you remember? Yeah, good.
xk plus grad of f at xk. 100 half.
Yeah. And the Hessian. If it's going to be exact, I have these tensor terms as well. Tensors freak me out, so I never write higher order approximation of functions. So I stick to Hessians. So I get rid of this. Now, so I've come up with the second order approximation of the function in the vicinity of xk. Now, if I want to see in this vicinity of xk what is the smallest value of this approximate function, how would I do it? I would take a derivative with respect to p, right? And that would give me the smallest, the minimum of this local approximation, right? Do you guys see what I'm saying? So let's call this m of p. So I set grad of p equal to 0. What do I get? Take derivatives. It becomes grad of f of xk equal to p, right? Took derivative with respect to p. So if I solve it, what do I obtain? Is the Newton step, right? So this is another way of driving the Newton step other than the Newton-Raphson type idea of root finding. So what does the Newton step tries to do in every iteration? More, do you know? Equation of what?
I just understand the equation perfectly.
Okay. You just understand that. What does this equation try to show?
In my mind, I think it's want to optimize this function. So we want to find the xk and p relationship.
Okay. What does this thing say is if I'm at a point, guess point xk, and I construct a quadratic approximation of the function, the Newton's direction is the direction at which this local approximation is minimized. So I'm at the, construct some approximation, I move to the minimum of this approximation, construct another approximation, and keep going forward. Last week, we derive the Newton steps using Newton-Raphson root finding idea. We end up with the same set of equations. So there are two ways of interpreting Newton's method. This is the second way. This is the way that we are going to use now to construct the general family of second-order method, quasi-Newton methods. Now, as I said, this is using Taylor's theorem, but I can come up with another type of approximation. I can replace this with some generic matrix BK. So your name was Achnia? Achna. Okay, I have to, sorry. Achna suggested that we need a convex approximation of the function at each point when we talked about Newton's method. Now, a quasi-Newton method tries to do that, even though we haven't talked about convexity, but it tries to approximate the function with a shape that looks like this, the shape that looks like this. How does it do it? By enforcing that this BK is positive definite. So in general, the Hessian might not be positive definite, but in the quasi-Newton method, we assume we are approximating the Hessian with the positive definite matrix, which gives us something that looks like that, because these things are nice. You will see what we mean by all of these things next week, but that's some a bit of foreshadowing, because we can solve these things, find these approximations locally. Okay. And then we want to construct this approximation of the Hessian in each step so that hopefully we end up approximating the Hessian in a more exact manner every single time. So our approximate becomes better and better and better as iterations go forward. So we have to understand how to construct this sequence of Hessian approximations now. There are two observations that are going to play an important role. The first thing is, if I evaluate this approximation at 0, so it means p is equal to 0, it means I'm not moving away from xk, it's to be expected that the value of m of 0 is fk, because all these two terms disappear. And the gradient of m at that 0 value is equal to gradient of f. Because again, if I take derivative, this disappears, this guy will have a p element in it, this will not have anything, right? These two observations will play an important role in the next slide. So the minimizer of this local approximation, as we observe, is given by this relationship. Again, important observation is it is similar to Newton's method. The difference is we are approximating the Hessian with some other matrix. And we want to construct this sequence of matrices. Now, instead of calculating BK from scratch every time, ideally we want to tap into all the knowledge, all the information that we have collected along the way. So we don't want to construct an approximation every single time from scratch. So we want to use these consecutive models so that we can come up with approximation for BK. All right. Now let's consider the model at the next k. The only difference is now that the time index of k is k plus 1. We want to relate bk and bk plus 1 somehow. So that's the aim. So the first question is, what sort of requirements should I enforce on bk plus 1? So what we really want to see is the local approximation gives us the same gradient behavior in consecutive steps. So we want the gradient of the new approximation to be the same as the gradient at point xk to be f, to be the same as the gradient of f at point xk and xk plus 1. Because think of it like this. I have a function, I'm approximating, I'm tessellating, I'm putting things side by side to approximate it. I want these overlapping models to be consistent. That's the idea behind it. So I want them to have the same gradient. First, we know that the gradient at 0 at point fk plus 1, sorry, xk plus 1 is exactly grad of f at point xk plus 1. So one of these requirements is satisfied automatically. The other one, now we have to enforce it somehow, right? So if I have a model like that, I want to make sure grad of mk plus 1 at xk is grad of f of xk. What value of p should I, sorry. No, it's fine. What that translates into p? I know xk plus 1 is xk plus alpha k pk, right? I know this should have been, I have to, I shouldn't, I have to be more careful here. I leave it empty. I know when p is equal to 0, we get xk plus 1. What value of p should I plug in there to go back to point xk? I have to move back by this much, right? So I plug it in here. Moving back is moving in the other direction, negative of the step. Now I just plug in the values. That's the left-hand side of this derivative. I have to enforce this equality. So that's what we have. So if I just shuffle around, I end up getting this condition. Okay? So if we end up defining these two variables s and y, we are going to use these two names heavily in this lecture, but again, don't feel that you're married to the name of these variables. Understand what they mean. One captures the variation in the steps, in the guessers. The other one captures the variation in the gradients. So rewriting this condition in terms of s and k, we get this equality, which is known as the second equation. Okay? They are identical. Alpha pk is the difference between the consecutive steps in the iterations. I'm going to make a statement, and we go on a break. We come back to what this statement means. We say this, it is only possible, so only if, finding a definite, positive definite matrix is possible that satisfies this equality condition or equation only if the following curvature condition is satisfied. So we call it the curvature condition. Now let's have a break for 10 minutes. In the break, what you can do is you walk around, but at the same time think about this statement. Focus on the term only if, and think about why I can say what I'm saying. Okay, see you in 10 minutes. Good. So we were up to here. Now, can someone tell me what this statement means and why? So the aim is to enforce this second condition so that the gradients are consistent as we tessellate these models. Now, the other thing I want to happen is that I can find a positive definite B that satisfies this condition. So these are the two things I want to happen. Here a statement is made that it is only possible only if this condition is satisfied. This is possible only if this condition is satisfied. What does only if here mean?
If that condition is satisfied, it's possible.
Yeah, okay. That's if, because when I have how many of you looked up the logic references that I've uploaded to LMS? So one. Again, if you don't have the background in predicate logic and mathematical proofs, it's something that you have to go and familiarize yourself with, especially logic. It's very important. So if I have P, then Q, let's write, I shouldn't have done it like this. Pk is possible, I call it P. That's a logical true or false statement. This condition, I call it Q. So the statement like this, is it equivalent to this or this? Let's see if a democratic process produces results. How many of you say the first one? How many of you say the second one? You don't have any opinion? You do? Oh, okay. Good. At least tyranny will not prevail. Now, why is the second one? All of you said second, so someone tell me why.
Only if that condition is satisfied, then P is possible.
What is another way of writing it, stating the same statement using if?
If Q, then P.
So now, okay, if this, then this. Okay, it's good. So now, does it mean this is a sufficient condition for this, or is it a necessary condition for this? If Q, then P, is this guy a sufficient condition for P or a necessary condition for P? It's a sufficient condition for P. Okay? So can I conclude that if this doesn't hold, this definitely will not hold? No. It's a sufficient condition. Han, you look concerned. What's going on? You fine?
Yeah.
Okay. Okay, so far so good. So then if you are more comfortable with an if condition like that, it says if this holds, then I can always find a positive definite bk plus 1. Now why? Up to now we dissected the statement. No, but I want to say, how can I now show that this is true? I want to now prove this statement. What happens if I hit both sides of that equation from the left by S transpose? What?
Well, if BK is positive there's positive definite, then the left side is always positive.
Yeah. So if I enforce the positivity of the right-hand side, definitely the left-hand side is positive for any choice of SK, right? What did it mean? It means BK plus 1 will be a positive definite matrix. Okay? So we enforce this to get that. Again, it is important to try to interpret these conditions and understand why they are there. Otherwise, they just remain a list of conditions. You can memorize them, but that's useless if you don't understand what is the point of these conditions when you try to solve a particular problem. Okay, now let's go back to where we are. Now, if we call F is strongly convex, what it really means now, that's the first time we are assigning some algebraic meaning to this statement, is the Hessian of X is positive definite for any X. That means strongly convex. Strongly looks like a ball. The curvature condition will be satisfied for any point xa and xa plus 1. So we don't need to enforce it explicitly for a strongly convex function. This is not the case for non-strongly convex function or any generic non-convex function. So for the most general case of problems, we have to enforce this condition for consecutive iterations. So this limits our ability to vary the iterations. So we have to enforce this explicitly. But there is one good thing about it. We can get this curvature condition for gratis if we use Wolff conditions on the step size. Because really, what that curvature condition means is it gets translated to the second Wolff condition. Do you remember we used to call it curvature condition as well? So they are the same. One is consequence of the other one. So this is the Wolf condition, if you enforce it. Now if you add and subtract, or in this case, am I adding? Yeah, if I subtract, which one do I need to subtract? Okay, let's subtract. From both sides. I can factor out now this term. I end up getting this. Sorry, there's an alpha k here as well. Do I need an alpha k? Oh, the alpha k is missing there. So I always discover typos. Let's see. Yep. Is there a type? There's a typo there. Yeah, no, there should be an alpha k, but then there is a.
Is it alpha in this case?
SK is xk plus 1 minus xk.
Which is alpha k big K.
Yeah, but here I'm writing in terms of sk directly.
Yeah.
Oh, here it is. Correct. Yeah, you're right. Yes, so there's no typo here. Here I've written it in terms of pk here. So, correct? So if I now write it in terms of pk, because sk is alpha pk, this is together is sk, I end up getting this other condition. In Wolf condition, we enforce C2 to be less than 1. And because pk is a descent direction, then this term on the right is always positive. So we have the curvature condition satisfied. Sorry. Okay. Now, when the curvature condition is satisfied, the second equation has infinitely many solutions. Why is that? Because the second equation, does it have more unknowns than equations or more equations than unknowns? How many unknowns do we have? If we are in an n-dimensional space. Sure.
N squared.
Fewer than that.
Is it symmetric? Whatever the top triangle would be is.
It is n squared divided by 2 plus n. I mean, n squared plus n divided by 2. Yeah. But those many. How many equations do we have? N. You have n equations, right? What is the dimension of y? It's the same as the space. So how many, do we have more unknowns than equations or more equations than unknowns? We have more unknowns than equations. So if you have a system of linear equations, and they are linear, that has more unknowns than equations, how many solutions do we have? Infinitely many solutions. Okay? So there are infinitely many solutions. If this condition is satisfied, that are positive definite as well. It's good. Now, a sensible person can ask a question of all these infinitely many solutions, which one should I pick? So a bunch of people in the 60s decided to answer that question. They decided to say, okay, let's put a criterion, find this pk under some criterion. So of all the symmetric metrics satisfying the second equations, and we know that because we don't need to worry about the positivity, we can always find something. So they suggested, let's find the closest next approximation to the previous approximation in some sense. So if I come up with a guess for the Hessian and I move a bit, the intuition was that my Hessian should not change too much. So my approximation of Hessian shouldn't change too much. So let's find something that is close to my previous approximation that satisfies the second equations. And it's symmetric. Okay? Here I put it, I said close in some sense. Whenever I hear closeness in vector spaces, automatically I think of norms. I mean, that's the majority of people think of norms. Here I'm not specifying any type of norm. So in general, different choices of norm here will give rise to a different versions of a quasi-Newton method. What do we mean by being close to the previous B? So you can generate infinitely many algorithms there if you recursively keep solving this optimization problem. Now, up to now, what is the silliest thing you've seen in the lecture today? This is the silliest thing you've seen. Because we want to solve an optimization problem. We are going to estimate the Hessian. But then I am asking you to solve this other optimization problem that is potentially more difficult than the original problem I'm solving. So what is the point, right? Again, it's something else. Think about things that you see. Okay. So before going forward, what can save us? What can we hope?
For some reasonable norm, there's a closed form solution.
Yes. That we can solve this problem efficiently in a closed form solution if we are careful about the choice of norm here. That's the underlying message in the Broyden class quasi-Newton methods. There are choices of norms there that make our lives very easy. So that's the useful norm that we hope to see. It's called the weighted Frobenius norm. Okay. The choice of W in general can be any matrix that satisfies that particular equation. What is that particular equation? It's the inverse of the second equation. If I just hit bk by both sides, that becomes W on the other side, right? It's the other way around. Then, of all the W, again, just before going forward, who hasn't heard of Frobenius norm? Okay, good. So, Mark, you've heard of Frobenius norm. Can you just briefly tell us what it is? Okay. If I concatenate all the columns of the matrix on top of each other, what do I end up with? It's a massive vector, right? if I take the L2 norm of that massive vector, is the Frobenius norm. Or P2 norm, depending whatever you want to call it. So what it is the sum of the squares of every single element of a matrix. Now I can weight this. Now we can weight it like that. Now W to power half relies on W being positive semi-definite. And we can decompose positive semi-definite matrices into the products of two other matrices. So that's what that thing is. Now, the other question I wonder, how many of you have done a linear algebra subject in their undergrad? And they didn't cover Frobenius norm? My guess is that you've forgotten. Because again, it's one of its. I can see a basic linear algebra subject not covering operator norms. But Frobenius norm is a very simple norm. So I don't know. I would have expected that you've seen it in a basic subject. But again, conceptually, it's not very difficult. Now, if we choose W to be this made-up matrix G inverse, and define G as the average Hessian, so we take the average variation of the Hessian between consecutive steps. So xk is where we are. Xk plus alpha k pk is the next step. If I take the average of the Hessian along the path, that's how I construct gk. Because 0 is where we start. For tau equal to 0 is where we start. Tau equal to 1 where we end. So along that path, if I take the average of the Hessian, that's how we define G. Now, the most important contribution in designing the DFGS method, or here is the DFP method really, but these sort of methods was the observation that those Frobenius norm, we have to use a weighted Frobenius norm, and if we pick this particular weight, things suddenly become very easy. That was the contribution. The derivation is very simple. In fact, you can drive the rest, this thing, half a page of algebra now. Now, let's see. Then, using this definition, we will observe this, and really it follows Taylor's theorem or a fundamental theorem of calculus. You can invoke both of them to show that. And if with this choice of a weighted norm, we end up getting this closed form solution for bk1 given the previous step bk and all the other problem data sk and yk. Now what I suggest that you go, and I think that might be even in the first. No, is the homework for the second one? I don't know. If one of your homeworks is to drive these sort of solutions, start thinking about why we can do this. To be able to now, we need a bit more machinery to be able to drive it, but then I think in your next one or the one after, we come back and one of your homework questions is to derive this expression, and you will see how simple it is. Now, this formula is called DFP. 3 other people. The next one is Powell. Oh, here we go. Originally by Davidon, but then Fletcher and Powell popularized it, and it goes back to 1959. It's a very old established method. So it really, what it does, it estimates bk iteratively. And then when we estimate BK, what do we need to implement the Quasi-Newton method? We need BK inverse, right? Right? We need BK inverse. So we can construct BK recursively, but then if we are going to take this method every single step, we have to calculate the inverse of BK. Can someone tell me what is the computational complexity of inversion? It requires n cubed number of operations. N is the dimension of space. For certain, if we are very efficient, we can try to bring it down to, I think, 2.5. But in general, it's n cubed. So it's a hefty set of operations. We probably don't want to do it. So the next question is that, is it possible to use these updates but efficiently calculate the inverse? So we don't need to explicitly calculate the inverse of BK at each iteration. Before giving you the answer, let's look at these sets of equations. Let me write it in an expanded form. Can I write it in an expanded form? Yeah. If it's useful or not. I'll go. Oh, no, it's good. I won't write it in expanded form. There is another way of writing it. I call this thing V transpose. I call this V. I call this guy, I don't know, C. Let's assume I have access to the inverse of BK. Does anyone remember a way to efficiently calculate the inverse of BK plus 1? The solution is the matrix inversion lemma. Woodbury, Sherman, Morrison, etc., etc. So it's a general statement. It's saying, it says, if I have a matrix A, whose inverse I know, and A hat is constructed by perturbing A by something, UV transpose, then the inverse of A hat, is given by this formula. So it's a known fact. So if we use that, we had to expand it. And expand that update, we end up having BK plus two matrices multiplying each other. We end up getting, and applying the Sherman-Morrison-Woodbury formula, we get an update rule that looks like this. Again, work it out. It's just algebra. On its own, it doesn't shed any insight into anything. It just warms you up in doing manipulations. So as we will see from this update, if H is not inverse of BK, I even don't need to explicitly calculate BK anymore. Because in the iterations, I work with the inverse of BK. Here we call it HK. So I start from some inverse, I use these updates, get the next inverse. Iteratively, now I have something that keeps calculating the inverse of the BK update from the DFP formula. Observation is that HK undergoes a rank 2 update because it's a rank 1 matrix there, and this is another rank 1 matrix there. The denominator is scalar, these things are rank 1 matrix, this is another rank 1 matrix. Now, if I say a rank 1 matrix, how many of you don't know what I'm saying? Okay, so all of you know what I mean by rank 1. So it's a matrix whose rank is 1. It means all its other n minus 1 of its eigenvalues are 0, has only one non-zero eigenvalue, and one corresponding eigenvector. And it can be written as the outer product of that particular eigenvector, because it's symmetric. Okay? Again, if you shouldn't be shy if you don't know something, but if in case you're shy, that's the definition, but go back and look at the definition of rank. Okay. So really the take-home message is instead of recomputing the approximate Hessian or their inverse from scratch every single time, we can apply a simple modification that combines the most recent observed data with everything that we know. So we keep embedding. We don't need to store everything in the past. We combine things as we go forward. And this gives us an update for our Hessian approximation. Now, depending on your background, how many of you have done an advanced control subject? How many of you have seen state spaces? Okay. Richard, do you remember the definition of state? Does anyone remember the definition of state? Okay. State of a dynamical system contains all its history. So to be able to know where it's going, I don't need to remember anything in the past. Okay? So that's that. Again, in a hand-wavy way, it's like a Markovian property. For the next step, I don't need to know anything about the past. I only need to know the current step. So that update is similar to it. I only need the information to be able to construct the next H. I only need information about H and all those other variables at that time. Now, again, in a dynamical systems point of view, H is the state, Y and S are the inputs. It's a nonlinear system, but that's how it is. Okay? So that's one observation. Another observation is really an estimator. It's an estimator for an unknown state. That state is the Hessian of another dynamical system. So that's somehow you can think about it in dynamical system language. Okay, in DFP we constructed iteratively the Hessian, then we used the Woodbury formula to construct a recursive version of the inverse and implemented it. There is another way of thinking about this problem. Instead of constructing the Hessian, because we never used the Hessian explicitly and directly, we might as well construct an estimator that estimates the inverse of Hessian directly. So I want to iteratively come up with the inverse of a Hessian that is closest to the previous inverse of the Hessian that satisfies now this other version of the second equation. Is the other way around. Is it the other way? Yeah?
Isn't that what we just did?
We constructed the Hessian inverse Hessian. Yeah. And then use this to invert it. So we might as well construct the inverse of the Hessian directly. With the same choice of Frobenius norm, weighted Frobenius norm, the same choice of W. Now this time W is GK instead of GK inverse. And the same sort of algebra, we can end up with this iterative update as well. They look very similar because they come out of the same sort of machinery. But now we don't need to worry about the Sherman-Morrison update anymore. And it has another nice property. Because in using the Sherman-Morrison update, HK would have appeared in the denominator of the updates. This guy, H only is in the numerator. It's only in the linear form. So in H, the updates is affine. Here in H, the update was not affine. So it's nice. Anything that's affine is good. Affine, do you know what I mean by affine? It's something that's linear plus some bias. That's an affine map. Okay, so numerically this is a nicer method. And in practice, using BFGS yields better practical results as well compared with DFP and then using the Sherman-Morrison update. Now, one good question is, how do I initialize this sequence? How do I pick the initial condition? No one knows. So it's a bit of a letdown. It's elegant up to now, but I don't know how to initialize it. You can come up with different guesses. If you have knowledge about the initial real Hessian, so you might as well initialize it with the real estimate. Then the trajectories remain close. But it really depends on different scenarios. One common way of initializing it is just we initialize it with some multiple of identity, for instance. So a simple implementation of the BFGS algorithm would look like this. Start from some initial guesses for H and X, some tolerance epsilon, and then keep updating, find the search direction P, find the step size, construct these variable yk, sk, rho k, do the update on H, repeat. So that's a very simple implementation of BFGS method. Now again, we have to have some observations. Each iteration, per iteration complexity is n squared, because we are only multiplying matrices and vectors. And that's these are n squared operations. We don't have any n cubed operation because we are not inverting any matrix. And we are not multiplying matrices. The algorithm is numerically robust. It's an empirical observation. And if it converges, it will converge superlinearly fast. It's nice. Okay. Now, some observations, and we will see a bunch of numerical examples quickly. Even though Newton's convergence is quadratic, that's not the whole story. Because, again, in the first lecture, I said, imagine you design an algorithm that gives you a solution in one step. But that step takes 10 million years. It's a useless algorithm, right? Because even though convergence rate is fast, per iteration complexity is nuts. So we don't want that. Now, but let's try to compare these things. Newton's method is quadratic, so it converges in very few steps. But per iteration, we have an n-cubed order of operations because we are inverting a matrix somehow, either with factorization, singular value decomposition. Somehow, we are inverting it, and that's n-cubed operations. If the system doesn't have a particular structure, banded matrices, etc., etc. Now, if H is positive definite, HK plus 1 is positive definite too. It is easy to see because if I go back to the updates, I was going to close it on the screen. Where was it? You can try to. I mean, there are different ways. If I hit it from the left and the right, you can show that the spectrum remains positive. So the iterations remain positive. We always end up with positive definite estimates if we initialize it as a positive definite matrix. Yeah. If you multiply both sides by some arbitrary vector, you'll see it. Do it. I mean, you can do it here. Multiply both sides by some x. And really the reason is because of the presence of this rho k. It makes some scalars less than 1. I mean, you guys do it. If you can't do it, come and ask me next time. Try to show that if we initialize these iterations with a positive definite matrix, for anything in the future, HK plus 1 remains positive definite as well. Just multiply it by both sides. Again, it's an empirical observation. If HK estimates the curvature incorrectly in the beginning, it tends to correct itself. So in the language, again, dynamical systems, the observer or the estimator that we've constructed is asymptotically stable. So that's what it means in the language. I have not seen any formal proof of this statement. But it seems to be the case. So if anyone can show it, that's a big contribution. In practice, DFP doesn't exhibit the same sort of behavior. And my guess is because of the non-affine, because the updates are non-affine in H in the end. And these self-correcting properties are only observed when adequate line search is performed. So we've done both the R-mu condition and the curvature condition. Okay. Now let me show you some numerical behavior. Hopefully it won't crash. Sometimes it does. Okay. So what I'm going to do, I'm going to solve some problems using BFGS, a Newton method, and some off-the-shelf solver. Okay? The off-the-shelf solver is written by very smart people, but it's written as a general solver. Okay, now let's see some stuff. I have to bring a bunch of things in. It's good. Now I think the number of my variables are 100, I think. And the cost function looks like this. So here I picked n to be 100, m to be 700 for no good reason. Just it's an example, right? I want to show you stuff. I set up some things. I don't know if I did it. I think I did. I don't know. Yeah. Now let's see how the Newton's method is going to implement. I have stuff here. Okay. Then I set up the BFGS method. And then I'm setting up the off-the-shelf solver by UCLA people. And now let's compare them. I am limiting the number of iterations for Newton to be 500. We will see that we will get the results in fewer steps. I'm putting it 1,000 for BFGS. We will see that we need more steps, but we don't have more time. And for the off-the-shelf solver, I put 100 iterations as well. We will see we will converge in as many steps as the Newton step. But just that. Now let's start. Okay, it doesn't matter the first one. Now I want to have this feeling of waiting. So I'm showing you the function value, some ridiculous number, doesn't matter, and some gradient. the norm of the gradient. So the norm of the gradient is not really changing much. It's to be expected. But I've done it a few times before, so my prediction is when we hit around 20 steps, suddenly you will see a big change. But we have nothing else to do with our lives, so we might as well sit here and stare. You can do other things. Think of it as a break, but I want you to see when it starts changing. And each instance of the problem is random, so I mean, maybe I should have constructed one instance that I exactly knew how it behaves. It's surprising to me. It's exciting. So already, we can hope things are changing, right? We spend from here to here around 58, but then we spend this much in 57 region. Now we are spending 2 iterations in 56, 55. Now let's see what happens in the next one. So we jumped. So these, we are getting smaller faster. But we haven't hit the quadratic convergence region yet. We are just meandering around, slowly getting to the solution. Now we probably will see bigger and bigger jumps. Still, we haven't hit the quadratic convergence domain. I wanted to have a feel of each per iteration time as well. There's crescendo into this moment. That's the moment we waited all our lives. Good. That was unexpected. That's fine. It's one of the longest ones. Okay, these things happen because we are not always going, it's not a monotone decreasing sequence in Newton method. But have no fear, it's good. Okay, good. So suddenly we jump from there to here. So really, quadratic convergence kicked for this example, the random generator example, kicked in there. Now let's look up BFGS. Now we saw it took, I don't know, 50 steps. So for this problem, probably BFGS will take 5,000 steps. But we only run it for 1,000. But now look at the magic of each iteration. Bang, 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 bang. And we are starting around the same initial condition. But this is all over the place. It's crazy. But it keeps coming back down. It's nuts. The key is not to pay attention too much to this now. And go and look at here. This is decreasing. So we are still finding it's not behaving terribly in terms of decreasing the value the cost function, but the norm of the gradient is all over the place. Which is, again, we never stated anything about the norm of the gradient for the quasi-Newton methods. And it has generated, I don't know, 160 iterations for the time that took the Newton method to generate, I don't know, 5 iterations probably. Now let's try to compare stuff. Again, it's not, you can do these things a bit more precisely, but here I really wanted to have a feel about all this, what convergence means, what pair iteration complexity means, etc., etc. Okay. So pair iteration complexity is how many arithmetic operations, orders of arithmetic operations we need for each method. I have the Newton methods, and then I have BFGS. Here n, so pair iteration here is n cubed. BFGS is n squared. In this example, n is 100. So this translates to how many iterations, how many operations, sorry? 10,000 operations per iteration, right? Sorry, no, another 100. 1 million iterations, 1 million operations. These translate to 10,000. Okay? So there is an break-even point in terms of clock on the wall time, real-world time, of when one is better in terms of performance in real time, from a real-time point of view. Well, let's keep going. Let's see where we are. So going strong. So what is how can I look at that? That's where the rate of convergence plays a role. For example, the break-even point is, now as I said, for many problems, they happen to be around the same time. I'm not taking it. If the Newton methods There is another concept of complexity as well. They call it oracle complexity. It goes back to how many calls to the oracle do I make? So how many iterations do I need to go to converge? We will come back to it in a few lectures, but let's just see it. So now let's call it oracle complexity. For different methods, there are different things. In oracle complexity of Newton method, it is independent of n. That's one good thing about it. It doesn't depend on the size of the problem. It depends on other things. And let's say it is m steps. Okay, here I just terminated it. I am minus 38,000. If you go back to the solution we got out of Newton, you will see how far off we are. We need to go another. The solution was around minus 40,900. BFGS ended up there because I've terminated it. Otherwise, it would keep going for around 5 times more iterations. Now, oracle complexity of Newton, let's say it's capital M. BFGS is a lower order method. It will depend, it has some dependence on n. And it will depend on some other elements as well. Let's call this, now, we don't want to make it too complicated. Let's call this M1, call this M2. Can someone just, the back of envelope calculations, tells me if they are going to solve a problem and they want to pick the most efficient method, and let's assume they've done the calculations, know M1 and M2, when should they use Newton's, when they should use BFGS? You should go and multiply. So M1 times, I have to do 1 million iterations. I keep saying 1 million operations. M2 times, I need to do 10,000 operations. I pick the one that gives me the smallest number. So when we say Newton method is fast, we have to be a bit more careful what we mean by fast. It's fast in terms of number of iterations, but it might be slower in terms of real time. And we couldn't answer these questions without spending time understanding the underlying properties of these algorithms. So I beg you to think about these things when you're designing an algorithm, ever if you're thinking about finding a solution. Now, let's do something else. Let's use the off-the-shelf solver. Now, a very important disclaimer. Now, let me just press it first. Oh, God damn it. What happened? What have we done? Now, what is this? What did I set it up? I'm trying to understand what's gone wrong with this. What is ABC? Oh, okay. I think if I read this.
Did either modify A, B, or C?
Yeah, they all of them use A, B, and C. So that's good. I mean, I defined those.
Take deep copies if you want. Like, there's dot copy in a couple of places. I don't know what modifications you'd be expecting.
But they never update A, B, and C.
Looks like it's an uninstall.
You might have just failed to solve it for some reason and then tried to call the solution out of some structure that never got done.
Yeah, maybe that's the problem with it wouldn't be apple and oranges. I mean, it would be a bit of an apple and oranges comparison if that's the reason. But let's see. That was that. It's a different instance of the problem that was there. I mean, it was initializing at a weird point. It couldn't solve it. Now, something I want to... The disclaimer is, I'm not saying people who wrote this package were dumb. I'm saying they wrote a generic solver that you can... It's an off-the-shelf solver that you can take anything, plug it in, and it will give you a solution. The Nielsen method that I wrote, I had written it for that particular problem. So I had used all sort of, without thinking too much, it's not the most efficient implementation, but I had used the structure. So now just how long it takes to generate iterations. We even haven't get past the first one. This is just the setup. Now, it's another important thing. Using off-the-shelf solvers, they might be useful because people spend time to develop them, they test them, but by construction, they work for a broad family of problems. So they are not, most of the time, they are not designed, here we go, the first iteration. Most of the time, they are not designed to take advantage of things that can be taken advantage of if you think about your problem. That's why they are slow. Again, most of the time. So as an engineer, because I think everyone here is an engineer, and I'm using this concept of engineer as a real engineer, not enterprise engineers that everyone's popped to. Someone who thinks about solving problems properly, that's what I mean by an engineer. Sometimes you're better off to if you spend some time to understand the problem and come up with your own solution. It might sound like a very obvious thing to do, but a lot of people don't do it. So the amount of effort that you put in to understand the problem will pay off in the end in terms of real performance. Again, unfortunately, a lot of us don't tend to think like that. We are just comfortable with picking things off the shelf, just put them together, and voila, we get a result, but we don't understand why. So if one outcome comes out of this subject, is this message. It pays off if you think about the problem that you're trying to solve. And it pays off if you think about it in a systematic way using the appropriate tools. And when you compare things, you make sure that you're comparing them properly.
So, if we use the Newton method, if we use that, that means it's just for some special problems, then it could be very fast. But
Yeah.
if normally we use BFG,
No, I did not say that. I did not say that. You have to make the comparison all the time, looking at the big picture. Newton might be good for a set of, in the real-time performance, might be good for a set of problems. BFGS might be good for another set of problems. I cannot make a statement saying most of the time BFGS is better than Newton. I cannot make that statement.
And which method is the CVX utility using?
It's probably using a version of Newton. Because if I run the Newton method for the same instance of the problem data, the number of iterations are the same.
Do you provide a function?
I provide the same set of information to because I provided with. I gave it the Hessian and the grad. So I use the same set of. I don't tell it to do numerical computations. But again, the point is, that's the main point of this. That's one point. Compare things knowing everything, and then using the off-the-shelf solvers. For small-scale problems, it won't. For really small, mini problems, it wouldn't matter. But as these things become bigger and bigger, I'm using only 100 variables. These differences will become bigger and bigger as we look at bigger problems.
But how can we compare the method before we apply them?
Okay, now there are different ways of looking at it. Either we can spend time doing theoretical analysis, coming up with oracle complexity results, which is possible. That's one way. So given a problem, you can go and using the tools that hopefully we will get you can come up with estimates of M1 and M2.
So this is from theory.
Comes from the theory, yeah.
M1, M2 is from the
You can come up with estimates of it from theory. That's one thing. But then, in a lot of problems, we need to solve an optimization problem over and over. So if we are lazy, we don't want to do the theoretical work, we can go and run a lot of tests numerically. It is less satisfying, and probably you can not rely on it too much, but now you can have another set of estimate, which is empirical estimate. Run it for a battery of tests, come up with some average values, then use that to design. I don't expect everyone to spend a lot of time always deriving solutions, but we have to understand where they come from.
How did you initialize the BFGS here? Did you give it the real Hessian?
Yeah, I can't remember.
Because earlier you said if you give it the real Hessian, the trajectories may remain close.
Yeah.
Which seems weird that it would take 100 more.
I give it the real Hessian.
And it would still take 5,000 versus 50 iterations.
Yeah, something in that order.
So BFGS doesn't like collapse to Newton's method if you give it the correct info.
In the limit, it does collapse to Newton's method, but getting to that limit. So the last, 100 iterations of BFGS, and that's how a lot of people prove the behavior of BFGS. Eventually, it ends up becoming Newton exactly. But that eventually is the key. Okay, this thing is still going. Okay? Let's go back here now. I'll keep you updated whenever it's finished. So whatever line search algorithm we choose should always try step size alpha k equal to 1, because that's where we get the best convergence behavior. If alpha equal to 1 works, stick to that. That's just something to know. But in practice, we might do a fairly inaccurate line search, so we don't need to really shrink the step sizes with small amounts. Just get a coarse line search. As long as the line search satisfies the Wolf conditions, you're fine. For BFGS, we use these sort of, again, they're empirical. There's no reason behind them. People have been doing it for 5 decades. They realize these are good numbers. So that's what it suggested. We can initialize it as some multiple of identity. There is another way of initializing it by initializing by this value, the initial rank 1 variable. BFGS will not work properly if we don't enforce Wolf conditions in their entirety, so RMIO and the curvature. For example, if you only implement RMIO, we might not get a good result in the end. But if you go back and look at my BFGS implementation, I just implemented RMIO. It was fine, but we cannot rely on it too much. Now, in terms of convergence, as I said, BFGS doesn't have a general sort of result. It relies on a lot of assumptions on the cost. But what we have is this. But let's just say the statement, then we talk about the things on top. And this thing is still going. So the idea is that if F is nice, if we end up B not to be any symmetric positive definite, so the initial point is, initial guess is a symmetric positive definite, and locally the function is convex, so it's nice. Locally, again, we will see this. We'll spend the whole next week on this. And furthermore, it's even better than just convex. It satisfies this other inequality. So the Hessian, here we use gamma. The Hessian is lower and upper bounded by M and M. So its singular values are bounded from both sides. So it is strongly convex. Then the sequence that is generated by BFGS will converge to the solution. So if in the vicinity of the solution, if every function looks very nice, that's another way of saying it, BFGS method works. I'm not aware of other types of method results for BFGS. I mean, we can state other things, but they will degrade to just ordinary statements about steepest descent or any descent type of algorithm. I'm not aware of any results that talks about how these estimates exactly converge to the real Hessian. That would be very cool if anyone could do. But in practice, it seems it's happening, but we don't know why. And this thing is still going. And for those family of problems, these sort of problems, these properties, we can show that BFGS converges superlinearly fast. But we need extra assumptions. We need now the Hessian to be locally Lipschitz. So we need more regularity conditions. And we need this to be bounded. So what it really means is my distance to the solution, if I just sum the whole distances, is bounded. Under this condition, then we can have superlinear convergence. So these are strongish conditions. But again, in practice, it seems BFGS converges superlinearly. But these are the cases that we can prove it converges superlinearly. So there are open problems. There is a gap between the theory and what we've observed. Unless people recently have plugged this gap, I don't know. So that there is a bit of understanding that is missing in really analyzing these algorithms. Okay. I will do this. All right. Now, for a large-scale problem, if I have an n-dimensional if my decision variable has n is in Rn, how many numbers do I need to store to be able to implement BFGS? I need to store Sk. I need to store Yk. I mean, I need to store the previous value of the gradient. I need to store the previous value of x. So it's n plus n. I need to store the previous estimate of the inverse, which is n squared plus n divided by 2. So in total, I need n squared plus 5n divided by 2. So a number like this, right? Now, if n becomes very large, the requirements of just storing the data becomes massive. So if n, I don't know, has 1,000, not even, then 10,000 variables, and we want to store them as doubles, let's say, just the problem data will be in order of how many? So what is the requirement to store a double? 64? Yeah, it's 8 bytes. Let's just work it out. I don't know. It's 8 bytes. So 10,000 variables. It's the boundary of medium size to large scale. So 10,000 variables to power 2. We can work. We don't need to worry about the linear term, but let's just do it. What is that? I don't know. It's 4. It's a lot, yeah, right? Just forget about that. 4 times. Okay, so yeah, 400 megabytes, right? It is crazy. Even with our computers, you need to store that much in your RAM. So BFGS doesn't really scale well. Now there is one way around it. And not surprisingly, it's called limited memory BFGS. This algorithm still is going as well. Now, solving large problems, now we need to do something about it. So what we need is some simple and compact approximation of the Hessian matrix. Well, nothing truer was ever said. Now let's see why. So instead of storing the whole matrix, the Hessian, we end up storing things that can be used to approximate it. The way to go around it is to store a bunch of n pairs of n-dimensional vectors And then we lose something, we gain something, we get slower convergence because we sacrifice the accuracy of the inverse of the Hessian, and we gain memory. So really the idea is to use curvature information of a window of observations to construct a very localized approximation of the Hessian. And then we shift this window. So we only store the last 10 curvature information, 10 step, for example, curvature information. We move one step further, we discard the oldest one, we stack the new one, and use this whole set of data together. So that's really the idea. So we store the last m pairs of Sj and Yj. Again, practically they say use between 3 and 20. I don't know why. I mean, just observations again. I'm not even convinced. I just copied it from the book. I'm not even convinced that makes much sense. I would say it depends on the size of the problem, really, what makes sense or not. But that's what empirically is recorded again. And then you can think of it like this. If I'm constructing the estimate, if I'm interested in constructing the estimate at time k, I treat it like I run the iterations of BFGS for the last m steps, using all the information that was available to me. So I run these iterations over j. They happen at step k. How many of you have heard of moving horizon estimation? It's exactly that, to estimate. So we only look at the last m observations to construct an estimate. Yeah.
Weren't we using a state earlier that summed up all of the information in the past?
Yes, but to store that, we needed this much information.
So now you only store Sj, Yj for the last.
Yeah, and then we use it to run the iterations forward for each iteration n, each iteration k. I run it, I get the results using the last m iterations, I make a decision, I discard the oldest one, do it again for this new window. I move again, do it again for the new window. So at each of these k's, I have to come up with a new initial guess. Now, it doesn't make sense to use the previous value of h because the whole point was not to store the previous value of h. Okay? And then we keep doing it every single step. And then the new iteration, as I said, we discard the oldest vector pair, we repeat the whole process. So it's really a moving horizon estimation problem. Now, there are two ways of implementing it. That's the intuitive one that makes sense, but it's not the most efficient one. But let's just have a look at it. We look at the last m pairs of measurements that we have. We start with q being the grad at the current time, and then we keep adding things. It's really implementing these two iterations in two loops. Just the implementation of these iterations, and then in the end we get R. This R is the current estimate times the current gradient. The total complexity is 4 times m times n. M is how many pairs we stored. N is the dimension. Plus these many iterations. We can, if we start from a diagonal initial condition, we need to do n multiplications there. If we use a dense estimation, we use n squared. Okay? So this is the computation complexity of running this whole loop. Probably we do it like this. We start with diagonal. And now that's again another trade-off. If 4 times m becomes much larger than n, we haven't gained much in terms of per iteration complexity. So we have to do a lot of computations. So that's why we pick m's to be small. Smaller than, it's 4 times m to be less than n, hopefully. As I said, in practice, there are different ways of initializing. That's one way. Initialize using the best inner product approximation of the previous Hessian. So the whole idea is that instead of storing the whole Hessian, we store all these generator vectors and run the estimate forward in each iteration. Now, as I said, this implementation of that idea is not the most efficient one. But we will see. Anyways, that's end up being the limited memory BFGS implementation. We have to enforce Wolf conditions. And then this is really, we discard the oldest one, we add the new one, we add it to the stack, and we keep repeating it. Again, small m is bad. The best m is problem dependent. It's something. Depends on the instance of the problem. It works well in practice, and to be expected doesn't work well when the problem is ill-conditioned, but that would be the problem with many other methods as well. Ill-conditioned problems, they don't show favorable numerical properties. That algorithm still is running as well, so it hasn't given us the solution yet. Now, I said it's not the best implementation. There is a smarter way of implementing it. Now, this smarter way is very hard to explain it. The idea is to use outer products to rewrite those iterations. We can show that if we work with these objects, we end up getting the same result. The proof comes from induction. How many of you know what proof by induction is? Okay. How many of you looked at the references in the LMS on proofs? So if you don't know something, go and look it up on that reference. Anyways, we can establish that this yields the same results as the other algorithm. But the key idea, I want you to see the key idea, is this. The updates are done by writing iterations that look like this. A very tall matrix multiplying a small square matrix, multiplying the same thing transpose. Writing the iterations like this will give us a complexity that looks like that. Now, if m is small, this term doesn't dominate. You end up getting 2mn. So it's a different way of, the previous iteration was had an on squared there. But now, by writing it like this, we get a smaller complexity. The previous method called unrolling, because we keep rolling updates. Unrolling the updates. This is the comparison of complexities. So we reduce it by 1 factor in m. Okay. This type of implementation is done in Nitro and IPOPT. IPOPT is probably the best open source solver using these sort of techniques. This is what they used. Here I just talked about DFP implementation, but we can have the same sort of idea for BFGS implementation as well. Because you remember, the updates are very similar. We can have it for the BFGS updates as well. So that's limited memory BFGS. Okay. And now we just conclude today's lecture by talking about sparse quasi-Newton updates. So if my Hessian has a particular sparsity pattern, so certain elements of it are, if certain elements are 0, I want my estimate to have the same sparsity pattern as well. Because then I don't need to store those, anything that is 0, I don't need to store it. It's nicer, and I preserve the structure. Then in the estimation problem, we enforce the sparsity structure like that. So wherever that we know the Hessian elements are 0, we enforce them to be 0 in the estimator as well. So we want to come up with the best estimate that preserves the sparsity structure of the problem. Okay? So it ends up solving a system of n by n linear equations that are sparse. Now this sounds super promising, but in practice the performance is garbage. The idea is great, but it doesn't translate well in practice. So it seems taking advantage of sparsity doesn't help us, which is a bit counterintuitive. So this is another open problem to think about maybe. How to have sparsity preserving BFGS type methods that have acceptable numerical performance. But there is another family of problems that are very useful. I mean, BFGS can do interesting things with them, are the partially separable cost functions. First observation is, if I have f that is a sum of a bunch of fi's, so these appear a lot in a lot of learning problems and least squares estimates. A lot of problems have that sort of thing, that we have the same set of decision variables, there are different functions. First observation is that if I take the Hessian, the grad is the sum of the grad and the sum of the Hessians. They are linear operators. It's fine. So the question is that, is it more efficient? So instead of storing this big Hessian, store the little Hessians of these, each of those FIs. Yeah, is it more efficient? Yes. But let's try to approximate each of them instead of approximating the whole Hessian. That's really the underlying idea. So what we do is this. For each Fi, we identify how that Fi depends on the variable in x, because those elements of x might not appear in every single Fi. For example, the first Fi, let's assume x has 4 variables, and I have 2 FIs, F1 and F2, and let's assume x has 3 variables. So it is x is x1, x2, x3, and F1 of x is really just x1 plus x2 to the power 4th, and F2 is x2 power 3 plus x3 squared. So these f's, they share the variable x2, but they don't have access to x1 or x3. So we can have a transformation that really just rewrite it, say, okay, for example, in this example, f1 only depends on x1 and x2, so I can rewrite it as saying f1 of x is really phi of 1, 0, 0, 0, 1, 0 times x, right? It only depends on x1 and x2. So I pick those 2 elements alone. So we call it compactifying matrix in this context, but in general they are called selection matrices. We select the appropriate elements of X. So this is another example. Then I can just call them different things. I can call them Z now, right? Using chain rule, can take derivatives. We end up getting with these sort of relationships. Now, instead of constructing approximations of the overall Hessian, we can construct the approximation of the Hessians of each of those F's in that form, in terms of phi. So I call B bracket I as the approximation of the ith function. And using these sort of local variables, construct these things locally now. This will be showing that is in your homeworks. Why does the approximation look like that? Because again, it's not hard, but it's good to do these sort of operations by hand just to see why. It really, takes advantage of the separability of functions, because not all functions depend on each other, so we can now parallelize the computations. That's one way of coming up with parallel solutions now. There is a challenge. We cannot guarantee that these partial curvature conditions are satisfied, and we cannot enforce it. So that's the challenge from a practical point of view, to be able to implement it, and it comes from a theoretical shortcoming. But if we can find, if we are lucky and these things are satisfied, the implementation is nice, because, as I said, we can now do all these estimates of the Hessian in parallel on different cores on a computer. So they don't need to exchange information with each other, and then we combine the result in the end. There is another interesting question. There is the choice of this partitioning is non-unique. If I'm given a sum of functions, there are different ways of partitioning the function into a sum of other functions. One form might be better, might have better properties than another form. So that choice is non-unique, and it's not clear how we can do this, how we can separate these functions into other functions. The modeling language AMPL, based on some heuristic, detects the separable structure, but they are just guesses. There is no. These heuristics are constructed over years and some arbitrary choices, but I'm not aware of any systematic way of partitioning functions into some separable structure. Some problems come with this separable structure by default. For example, if we are doing this optimization to estimate distribution of something, some signal, using different sensors, the variables might belong to different sensors separately. So that's, the separability is enforced on us, but sometimes it's not. We have to pick some way of separating the cost function. All right. That's today. Next week we will talk about convexity. We'll talk about convex sets, convex functions, and we will reinstate all the optimality conditions for convex problems. And okay, if there is no other questions, see you next week.